Okay, so in this video, we are going to test for a unit root in 3-month Treasury bill data. I'm sorry, I shared to the whiteboard. I want to share it to my Jupyter Notebook file. So here, we're going to go ahead and import NumPy as NP, import pandas as PD. Let's import date and time. Now let's import the data reader. So from pandas, data reader, import data as WB. Let's import matplotlib pyplot as PLT, and let's do matplotlib inline. And first we'll need, let's go ahead and do stats models. So let's import stats models.api as SM. So this we can, now we can do regressions. And then for the T-bill data, the 3-month, you use the symbol DGS3MO. And this is the 3-month data. So if I go over here and type it in, you can see that it is a time series. So here on the Federal Reserve's website, so our data source is going to be Fred, and here we can see the data. And we're going to get, let's do 1985 to 2005. So it's going to be roughly this chunk of roughly this much data. This is what it's going to look like. So there's our symbol. We got the symbol. Let's get the get the data. We'll say 3-month is going to be our data frame. We'll use WB.dataReader. The name is going to be the symbol. Our data source is going to be Fred, and our start date for the Fred data source. Depending on what you're doing, you can just give the dates as strings, and it will know what you're trying to do. So this is going to get the data. Let's look at the first few rows to make sure it worked. So we got the first 5, and there we go. So this is roughly daily data. So now that we got the data, let's get it ready to do a Dickey-Fuller test. So let's just so we can get it in get it a little bit cleaner, let's create a blank data frame. Let's create a column named YT and set that equal to our 3-month, but we specifically want this. We want that column, and let's drop not in numbers because stats models can't do anything if there's nans in it. So after this, let's create another column. This one will be y of t minus 1. This is going to be y of t shifted back by or with 1 lag. Then remember, in order to do the basic Dickey-Fuller, you're going to do the difference between these. So this is going to be the dependent variable in our regression. So let's set this to be the difference between yt and y of t minus 1. And again, stats models can't run or can't do any regressions or anything if there are not numbers in it, if there's any nans. So we got to get rid of all the nans. Let's get rid of them and keep it in place. Or let's do in place equal true. So now we have the data frame. We've imported stats models. So let's do it. Let's run our regression. Let's say sm.ols. And for the y, for the endogenous variable, we'll give it y. So this we're not gonna do the Dickey-Fuller test. First, we'll actually run the regression to get the parameters for an AR process. So this is going to be the lag, so 1 lag, t minus 1, and we're going to fit our regression. We're going to print out the results. So reg.summary, and let's see what it looks like. So this, if you did not if you don't do the Dickey-Fuller test and you look at this, this is actually would lead you to believe that it is a good fit. But you can see that the coefficient for the first lag is pretty high. So even though it has a really high t statistic, it has a very low p-value. So this would lead you to believe that it's statistically significant and has a very high adjusted R-squared. If we look at it, it would lead you to, if you go by the model statistics only, it would lead you to believe that potentially a first order autoregressive model would work. But we know that it may not. Let's plot the data and see what it actually looks like. This is about what we saw on the Fred's website. So if you go by the model alone, if you look at it, it would lead you to believe that's statistically significant, that it may be a good model. But you can see that the coefficient for the first lag is pretty close to 1. So let's do a basic Dickey-Fuller test to see if there is a unit root. So we're going to do ordinary least squares. The y variable now is going to be the difference between y and yt and yt minus 1. So it's going to be a difference between the two periods. So we're going to do our dy column for and then for our x, we're going to do the add constant. So you have your constant, and this is going to be the first lag. So yt minus 1. We're going to fit. We're going to print the regression summary results. What happened here? There is no dy. There is no dy. Oh, so it looks like up here I did df instead of dy. You want that to be dy. Df was short for data frame. Dy would be the change in y. So now you see that it is you get the coefficient, you get the standard error, and it is a very low t statistic. So for the Dickey-Fuller test, the null hypothesis is that there is a unit root. The burden of proof is proving that there is not a unit root. So for this, you cannot reject the null hypothesis. You cannot reject the null hypothesis, even a 10% significance level. You still can't reject the null hypothesis. So there is a unit root, and 3-month treasury rates would be a random walk. And just to kind of be consistent with what we saw before, so this negative 0.0004 is your theta that you would have seen in the last video. This 0.9996 would be the beta. If we do, remember, theta would be equal to 1 plus beta. So to solve for beta, if we do 1 plus negative 0.0004. This should equal beta in the previous regression. So 0.9996, and it does. So that checks out. So this is consistent with what we did. So now one more thing before we end this video. So we did a simple Dickey-Fuller test, but for the augmented Dickey-Fuller test, let's from stats models we can import. So let's do from stats models .tsa for time series analysis. Stat tools. We can import the AD Fuller little package. So now we can do the augmented Dickey-Fuller test, and we can run it on our on our data. So let's do let's create a value. Let's do AD Fuller, and you have to give it the time series. So let's do DF YT. This would be our 3-month treasury rate without the NANDs. And let's look at the result. So you get a you get kind of a bunch of stuff. So in this, the first value is the ADF statistic. This is the ADF statistic. And here would be the p-value. This would be the p-value. And then down here are our critical, the critical values for a 1% significance level, 5% significance level, and 10% significance level. So if we plot that out, there's one way that we can make it look a little bit cleaner. you don't have to do this, but let's I'll really show you some code to do it. So let's do the ADF statistic is equal to, and then let's format it. Let's format it. We'll get the I'm sorry, we'll get the result. We specifically want the first value. So remember that was the this was the augmented this was the statistic. Let me show you here. So we print that. Then let's print the p-value. So let's say p-value. We'll do the same formatting or the same formatting techniques, and we will we'll show the result of the second element, the next element. This is going to be the p-value. So we run this. So now the p-value we know is 52%. It's a little bit different than the one up here. It's the one up here is the p-value is 25.7%. The augmented Dickey-Fuller test will give you 52.1%. So they're a little bit different, but they're a little bit different tests. And then after this, if you were to want to do it, then you can print the critical value, so 1%, and the critical value for that. So for us, our statistic is negative 1.52. So in this direction, it would have to be greater than or larger than 3.4. And it's not even larger than the 2.5 at the 10% significance level. So then with this, you can just do it with a loop. We won't really fool with that in this class, or I'm sorry, in this video. But so this was how you do the augmented Dickey-Fuller test in Python. In the next video, we'll go over we'll build a AR. We'll use stats models to create an AR model for the spread between mortgage rates and 10-year treasury rates. So that's it for this video. In the next video, we'll do a little bit more Python.